We're always hearing about these powerful antibiotics, the ones that can take on just about any bacteria.
Yeah.
But have you ever heard of the specialists? The ones that are really picky about who they fight?
Yeah, it's kind of like in the superhero world. You've got your all-powerful ones who can handle any threat, and then you've got the specialist with very specific powers for very specific situations.
Right, exactly. And in the world of antibiotics, that's where monobactams come in. They're like the sharpshooters of the beta-lactam family.
So today we'll be diving deep into these fascinating drugs.
And we'll be exploring what makes them so unique, how they work their magic, and why they're so important, especially when we're dealing with allergies or really tough infections.
So let's start with the basics. You mentioned beta-lactams, which is a huge family of antibiotics. So
Yeah.
how do monobactams fit into that picture?
Well, the first thing that jumps out is their structure. It's fundamentally different. Think of your classic penicillin. It has that double ring structure, kind of like a bicycle.
Got it. 2 rings. Exactly. Now, monobactams, they're the rebels. They've just got the one beta-lactam ring. Imagine a unicycle instead of a bicycle.
Okay, so 1 ring instead of 2, and that makes a difference.
A huge difference because that single ring structure is what gives them their unique properties. If you could picture Astrianam, it's the main monobactam, you'd see that single 4-sided ring, and then there's another ring off to the side, but it's not fused to the first one.
Interesting. So it's not just about having 1 ring, it's also about how that ring is connected or not connected.
Precisely. And that seemingly small structural change has major implications for how it interacts with bacteria.
Okay, so let's get into the action.
Mm-hmm.
How do monobactams actually work against bacteria?
Well, like other beta-lactams, they still mess with the bacteria's ability to build their cell walls. That's their protective armor. But monobactams, they're very specific in their approach.
They're not just going after any old cell wall.
Nope. They've got a favorite target, something called penicillin-binding protein 3, or PBP3 for short.
TBP3.
And this PBT3 is mainly found in aerobic gram-negative bacteria. So 2 things to unpack there. Aerobic means they need oxygen to live just like us.
Right, makes sense.
And gram-negative refers to how they react to a specific staining process in the lab, which basically tells us about their cell wall structure. So when Astrianam latches onto PBP3 in these gram-negative bacteria, it's like throwing a wrench into their construction machinery.
So it's disrupting their ability to build that cell wall.
Exactly. It blocks a crucial step called transpeptidation, which leads to these long, fragile bacteria that eventually can't hold themselves together and they just burst and die. It's a very targeted attack.
Wow, so it's like a sniper taking out a specific enemy.
That's a great analogy. So who are these gram-negative bad guys that monobactams are designed to fight?
Yeah, let's name some names.
Okay, their hit list includes the Enterobacteriaceae family, which has some real troublemakers like E. coli and Klebsiella species.
Oh yeah, those are familiar culprits.
Then you've got Pseudomonas aeruginosa, Haemophilus influenza, and Neisseria species. They're all on the list.
Sir. A pretty impressive lineup of bad guys.
Yeah, but here's the catch. Remember that specific target PBP3? Well, other bacteria, like gram-positive ones, think Staphylococcus and Streptococcus, they don't have that same PBP3, or at least not one that Astrianam likes to bind to.
So it's not effective against those guys?
Nope. It's like they're invisible to Astrianam, and the same goes for anaerobic bacteria. Those that don't need oxygen, they're off the hook too.
So it's all about that specific target PBP3.
Exactly. It's what makes monobactams so unique. They're not trying to be all-powerful. They're specialists.
Which makes them incredibly valuable in certain situations, I imagine, like when we're talking about allergies.
Absolutely. You hit the nail on the head. This is where monobactams really shine. You see, some people have severe, even life-threatening allergies to penicillins or cephalosporins.
Right. Those are other beta-lactam antibiotics.
Exactly. And because monobactams have that unique single-ring structure, they're much less likely to cause cross-reactivity, which basically means if you're allergic to one, you're allergic to the other.
So it's like they're speaking a different language that the immune system doesn't recognize as a threat.
That's a good way to put it. So for those patients, a monobactam can be a lifesaver. It allows them to get the treatment they need without risking a dangerous allergic reaction.
That's amazing. So what kind of infections are monobactams typically used for?
They're great for a range of gram-negative infections. We talked about those bacteria, so I think pneumonia, meningitis, sepsis, urinary tract infections, skin and soft tissue infections, intra-abdominal infections. It's a pretty broad spectrum within that gram-negative world.
So they're not just a one-trick pony.
Nope. And sometimes they're even used in combination with other antibiotics to broaden the coverage even further, kind of like a tag team match.
I like that analogy.
And there's even an inhaled version of Astrianam specifically for cystic fibrosis patients who often struggle with chronic Pseudomonas lung infections.
Wow. So they've got that covered too. That's impressive. But I have to ask about the elephant in the room, antibiotic resistance.
Yeah, it's the constant battle, right?
Right.
Well, the good news is that monobactams are naturally pretty resistant to many of the common bacterial defenses, those enzymes called beta-lactamases that some bacteria produce to break down antibiotics.
So they've got some built-in armor.
They do, however, there are some tougher enemies out there. Some bacteria have evolved these super-powered beta-lactamases like ESBLs, extended spectrum beta-lactamases, and carbapenemases.
They sound pretty scary.
They can be because those can actually break down monobactams, and bacteria can also develop resistance by changing their PBB3 target, making it harder for the drug to bind, or they can even use efflux pumps, which are like tiny pumps in their cell walls that just spit the antibiotic back out.
Wow. So it's a constant arms race?
It is evolution in action. Bacteria are always finding ways to adapt, and we're always trying to stay one step ahead.
It's fascinating and a little bit frightening at the same time. But before we wrap up, I'm curious about the origin story. Where did monobactams come from in the first place?
It's actually pretty cool. Astrionium, the main monobactam, was originally isolated from a bacterium called Chromobacterium violaceum. Imagine that fighting bacteria with a molecule derived from another bacterium.
It's like a double agent.
Exactly. But the astrium we use today is synthetically produced in the lab, so we're not relying on bacteria to make it for us.
That makes sense. So let's recap. We've been talking about monobactams, these unique antibiotics, with a single ring structure that specifically target aerobic gram-negative bacteria by going after their PBP3. This makes them a crucial weapon, especially for people with penicillin allergies.
Exactly. And their focused action really highlights a crucial point in this era of growing antibiotic resistance. We need more targeted approaches, more specialists like monobactams.
Right, because using broad-spectrum antibiotics all the time can actually contribute to the resistance problem.
That's right. It's like using a sledgehammer when you really need a scalpel. Monobactams show us that we can be more precise in our approach, and that's something to keep in mind as we develop new antibiotics and strategies for fighting infections.
It's all about choosing the right tool for the job. And sometimes the specialist is the hero we need.
Couldn't have said it better myself.
Well, that's all the time we have for today, but we'll be back next week with another deep dive into the world of pharmaceuticals. Until then, thanks for listening.
Thanks for having me. It's been a pleasure.